To design more reliable electromechanical components and delay wear out, several strategies can be employed, focusing on material selection, design principles, and reliability testing. Here's a detailed explanation based on the provided sources. Material selection. Hardness and toughness. Hardness. Selecting materials with high hardness can resist wear from abrasion and erosion. For example, ceramics like alumina and silicon carbide are highly resistant to wear and are suitable for components exposed to abrasive environments. Toughness. Materials with high toughness can absorb energy and resist fracture under impact or cyclic loading. Stainless steels and nickel-based alloys are examples of tough materials that can withstand high stress without failing. Corrosion resistance. Corrosion-resistant materials. Choosing materials that resist corrosion can significantly extend the life of components. Stainless steels, nickel alloys like Hastelloy, and certain ceramics and fluoropolymers are excellent choices for corrosive environments. Lubricity. Inherent lubricity. Materials with low friction coefficients, such as silicon nitride, and polymer composites like PEEK reinforced with PTFE, can reduce wear in sliding applications like bearings and seals. Thermal properties. High temperature stability. Materials that maintain their properties at high temperatures, such as certain ceramics and high-temperature alloys, can prevent oxidation, creep, and phase changes that accelerate wear. Design principles. Reducing stress concentrations. Encapsulation and shielding. Strategies like local component encapsulation and direct component shielding can reduce stress concentrations around rigid elements, thereby delaying wear and failure. Strain dispersion. Designing components to distribute strain more evenly can prevent localized wear and cracking. Proper lubrication and sealing. Lubrication. Ensuring proper lubrication can reduce friction and wear. For example, using oil-lubricated or water-flushed bearings can prevent dry starts and reduce wear in pumps. Sealing. Effective sealing can exclude contaminants that cause wear, such as dust and moisture. Thermal management. Thermal derating. Designing components to operate below their maximum temperature ratings can prevent thermal degradation and extend their life. This includes using heat sinks, cooling systems, and selecting materials with good thermal conductivity. Redundancy and robustness. Redundant systems. Implementing redundant components and systems can ensure that a failure in one part does not lead to overall system failure. This is particularly important in critical applications. Robust feedback mechanisms. Using feedback control systems, such as PID controllers, can enhance the stability and accuracy of mechanical control systems, reducing the likelihood of wear due to parameter variations. Reliability testing and standards. Design for reliability. DFR. Failure modes and effects analysis. Identifying potential failure modes and their effects can help in designing components that are less likely to fail. Physics of failure. Using POF methods to understand the underlying mechanisms of failure can lead to more robust designs. Standards and testing. Reliability standards. Adhering to standards like MIL HDBK 217 and IPC can ensure that components meet reliability requirements. These standards provide guidelines for material selection, design practices, and testing procedures. Accelerated life testing. Performing tests at elevated stress levels can predict the long-term reliability of components and identify potential failure points early in the design process. By integrating these material properties, design principles, and reliability testing methods, electromechanical components like pumps, valves, and sensors can be designed to be more reliable and have a significantly delayed wear out, ensuring long-term performance and durability.